Hello everybody, this is my great pleasure to see all of you. So today my presentation is about noble membrane-based processes for nutrients, energy and water recovery from source-separated human urine. So my co-authors are Federico Bolpin and Sharupun. So I have different topics to cover today. So first one is briefly introduced to urine priorities and treatment, research gaps in urine treatment for reuse, what are the aims and objectives of this study. So we first look at what's the water extraction from human urine, nutrient extraction, and finally look at the energy extraction from the salt differences and conclude this presentation. So let's look at the nutrient cycle. So we have a lot of nitrogen content in the air. So using the Haber-Bosch process, we produce urea and ammonia, and we consume our food, and then we discharge this kind of nutrient as a P, and then we also send it to wastewater treatment plant to remove most of nitrogen, phosphorus because of environmental protection. And when you produce your nitrogen using the Haber-Bosch process, we need to invest around $1.5 per kilogram nitrogen production, and after converting to the fertilizer, and we discharge to the urine as a wastewater and goes to the wastewater treatment to remove 1 kilogram of nitrogen. We we have to spend around $2 for this kind of contaminant. So we try to also look at the phosphorus. Basically, phosphorus is rely on the phosphorus rock. So we produce 1 kilogram phosphorus, almost $2, and then same cycle, and then it goes to the wastewater treatment, and then we need to spend $0.15 to remove the phosphorus. So that's the phosphorus nutrient. And then another problem is phosphorus rock is becoming depleting, so that we have to make sure next 50 years, 100 years to secure the phosphorus fertilizer. Let's look at the urine's composition in relation to domestic wastewater. Only 1% of the wastewater volume, about 64% of the excreted trace organic compound. However, the proportion of this nitrogen, phosphorus, sulfate are very high concentration, up to 70 to 80% of nitrogen, 50% of phosphorus, 75% of sulfate. So in general, concentration of phosphate is more than 500 milligram per liter. Nitrogen is 5,000 milligram per liter. And this can be easily collected, especially high-rise and public buildings. And benefits from the urine recovery is we can make organic fertilizer. So we utilized our P to produce the ammonia and phosphorus, potassium fertilizer, and this will help to our mining of the phosphate, also Haber-Bosch process, nitrogen production, fertilizer, and discharge of the residual phosphorus and conversion of ammonia to nitrate in a wastewater treatment plant, which will protect our environment in waterways. So this research focuses on how we can utilize the urine So we look at the membrane technology, how we effectively produce the fertilizer and produce the energy and water. So this is our presentation structure. Water, nutrients, and energy are our main concern. In this presentation, we utilize the hydrolyzed urine, diluted fresh urine, and then power generation using membrane bioreactor, fold osmosis, and then reverse electrodialysis process. So let's look at our first human urine goes to the nutrient recovery system. So we hydrolyze the urine and we utilize the hybrid MBL MD for the production of concentrated fertilizer, and distilled water has been developed. So we collected our urine and then biologically we processed the urea to ammonia nitrate, and then we concentrate using membrane distillation. So research questions are the odor and organics in urine removed? And second question is ammonia converted into nitrate? Is treated urine concentrate to a commercial fertilizer level? Is the final product effective in growing lettuce and pak choi plants? So this study was published in Journal of Cleanup Production. So this is our sampling point from our urine source separation basement. So we conducted with biological treatment to remove organics, acidification, ammonia to nitrate conversion, and then it goes to the membrane distillation to produce concentrate fertilizer and distilled water and some sanitations. And finally, we produced our concentrate fertilizer to grow some pak choi lettuce using hydroponic system. The MBL, the reactor was inoculated with municipal wastewater sludge and treated for almost more than 10 months. And then TOC removal of 98%, ammonia to nitrate conversion of 50%. Was achieved from this technology. Also, we concentrate using membrane distillation, and 95% of urine concentration was achieved with MD, and severe flux decline occurred after 80% of concentration. So you can see the water flux decreased as concentration increased. So you can see the color of different urine, and then concentrate urine color of this water. And MD permeate, so we found more than 98% of ammonia rejected and 99% of TOC was rejected from membrane distillation. We tested hydroponic using this system. Then we found out that all the urine fertilizer can be equivalent to grow the lettuce and pak choi compared to commercially available fertilizer. And based on this research, now we can answer that 98% of TOC removal and 50% ammonia to nitrate conversion can be achieved, and 95% of urine concentration was achieved at 55-degree rejection, ammonia over TOC more than 97%, and then others more than 99%. So they have a very good rejection of ammonia, TOC, other compounds, and severe membrane fouling occurred. Then urine contained all the essential elements to grow lettuce and pak choi, which is a suitable fertilizer. And then next, our challenge is about how we can utilized our water flushed toilet. The previous study, it was very pure urine without water mixed. However, in toilet, so they mixed with the water flushed, and then we look at the F4 photosmosis membrane, dewater this water, and then we want to selectively collect our fertilizer. So when you utilize the photosmosis membrane technology, so our questions are, can we dewat the real diluted urine? And can we recover nitrogen and phosphorus from real urine? Can we produce the marketable fertilizer from it? Can the process be economically viable? So this study, first we look at the phosphorus recovery as struvite, the urine, and combined with the magnesium, we produce struvite, so that this can be applied for the struvite phosphorus recovery. And then phosphorus removal, when you have undiluted urine with terms of 5 times diluted urine. So phosphorus removal is very high, almost 95% with undiluted urine. And then when you dilute your urine 5 times, so this phosphorus removal to produce fertilizer is about 75%, so decreased a lot. And we look at what's the effect of different reverse salt flux when you apply for magnesium fertilizer. So this is the how this magnesium goes to the reverse salt flux and then produce the struvite concentration. Also, low urea rejection to supply nitrogen to the fertilizer, so that we try to see how we can advantage the limitation of fertilizer-driven photosmosis. So we collect from this fertilizer through solution, so phosphorus recovery. At the same time, urea and ammonia rejection loss can be achieved from this process. So we tested the real urine volume rejection with commercial fertilizer. So water flux decreased when we increased our concentration. So we concentrate up to 52% using our fertilizer through solution. And when you increase your pH, and then you have a very high precipitation, which is the one of the problem for water flux. So when you have a urine concentration up to 20% at pH 7.5, so we found out the very high fouling inorganic compound on the membrane surface to reduce the this water flux. And this is the saturated solid, what's the struvite in terms of different temperature, how they form, and then this creates the precipitation of membrane surface. Real urine nitrogen phosphorus. So when you have this nitrogen phosphorus, so before treatment, the concentration of phosphorus was almost 400 milligram per liter. Nitrogen concentration was almost 3,700 milligram per liter. So after this hydrolyzed condition, and then we found out 93% of the phosphorus removal, and then 50% of this nitrogen removal concentration. And then we look at the solid precipitants, and then measured XLD, and we found out most of them are potassium struvite and ammonia struvite oriented phosphorus nutrients were recovered. So our question now can be answered from this study. So 50% of real urine concentration, 50% nitrogen recovery as urea diluted fertilizer, and 93% phosphorus recovery as just Struvite, with downstream wastewater saving into account. The return on investment met after 2 years of this application. So last section of this presentation is reverse electrodialysis to produce energy using salt gradient power based on the urine and then tap water system. So we try to apply RED system to convince what's the efficiency of our energy production from this urine. So how much energy can be recovered from this urine? Is urine sanitized when used as an electrolyte solution? Do the ion exchange membrane fall with real urine? Also, this study was published in Water Research and just a couple of months ago. So this is the very typical ion exchange membrane. So this is the RED process, anode oxidation and cathode reduction. So you have anionic cationic membrane to separate different ions in urine. So they are moving around while they convert, and then we have electrons produced from this RED system. So we utilize the urine as very high concentration urine, and then tap water as low concentration, and then try to look at what energy power can be produced, and we try to separate two different systems. One is the potassium cyanide plus sodium chloride, which is a very typical electrolyte solution, and then we look at the replacement of this electrolyte using hydrolyzed urine. Also, we just use as fresh and hydrolyzed urine as a single pass in the RED system. So how much power we can produce? The first system A for the replacement of this electrolyte. So real urine, we produced almost 1 to 0.8 watt per square meter using this RED system, and energy recovery for this maximum energy net is around 0.05 to 0.04 kilowatt hour per cubic meter using real urine condition. And then we found out based on this commercial electrolyte, then we produced this level of power density and then maximum energy net. And system B, we replaced our electrolytes and then look at what's the power density can be produced, and then this is very minimum power density around 0.1 watt per square meter, and then energy net is also very low compared to our system A, so 10 times, and the power density decreased using urine as electrolyte solution. And then electrooxidation using system B, we found out around 13%, 6%, 4.4% of the removal of TOC, ammonia, and urea from this RED system. So our question can be answered. Energy net from hydrolyzed urine is around 0.05 kilowatt per cubic meter. Urine could be used both as high concentration and electrolyte solution, but the electrolyte solution replacement is not really as efficient as commercial electrolyte solution. Up to 13%, 6%, and 4% of the removal of TOC, ammonia, and urea. So based on these three research approach to produce the fertilizer, water, and energy, I can conclude that different technology has a different merit. The first one is MBR and membrane distillation. So we achieved 100% nitrogen, phosphorus, potassium recovery as a liquid fertilizer, up to almost 280 grams per liter, and stable operation of nitrification of MBR. Also fertilizer through photosmosis, 50% nitrogen and 93% and phosphorus recovery was achieved from this F4 process, with average flux of 8 NMH and return on investment achievable after 2.7 years. The RED energy net from hydrolyzed urine is around 0.05 kilowatt per cubic meter, with some of the compounds, TOC, ammonia, urea, can be removed. So this is the possible application of our membrane using our urine resource recovery for fertilizer, energy, and water production. I'd like to thank you, Federico Burpin, was our resource recovery team at the University of Technology, Sydney. And if you have any questions, please email me. I'm happy to answer and then discuss and collaborate together. Thank you for your attention.